Um, okay, so imagine medical evidence as this uh, really intricate, sprawling city water system.
Oh, that's a good way to look at.
Right, like before a brand new, supposedly amazing purification filter is installed into the main municipal supply. It has to be rigorously, almost ruthlessly tested.
Yeah, you wouldn't just throw it into the reservoir and hope for the best.
Exactly. You put it in an isolated, highly controlled laboratory.
Hmm.
You run exhaustive tests to see if it actually removes toxins without causing secondary damage or altering the pH or, leaching heavy metals into the supply.
Right.
And that incredibly controlled laboratory test, that is the intervention trial. But let's say the filter works perfectly in the lab and you install it into the main system. How do you then deploy sensors across the entire city's sprawling, chaotic, century-old water grid to catch microscopic leaks before the pipes burst?
That is population screening.
Yes.
That is a perfect way to visualize it because today we are taking a structured, conceptual journey through two deeply connected, yet fundamentally different worlds of public health.
We really are.
We're tracing the entire path of medical evidence. We are going to map the journey from identifying a hazard and a risk, to tracking an exposure, to measuring an outcome, to testing an intervention, and finally, to witnessing sweeping system impact.
And for you listening, if you're following along with the Oxford textbook of global public health, we're using chapters 5.7 and 11.4 as our structural spine today.
Exactly. And the overarching mission of this deep dive is to see how we transform epidemiological reasoning into experimental proof under highly controlled conditions, and then, well, how we apply those proven interventions at a massive, messy population scale.
Right, we're going to focus heavily on differentiation. Our target audience today, whether you're a medical student prepping for boards or a junior doctor or a public health trainee, you already know the basics, so we aren't going to sit here and define what a placebo is.
No, we are going to unpack why decisions are made, the underlying mechanisms, and how to avoid the statistical traps that have derailed some of the biggest trials in medical history.
Systems thinking is going to be our guiding framework here.
It's crucial. We have to understand the stark differences between a hazard and a risk, between a true clinical outcome and a seductive surrogate marker, and perhaps most importantly, between opportunistic testing in an individual clinic and systematic screening rolled out across millions of healthy people.
We're looking at how changing an exposure changes an outcome, and how we measure that change without fooling ourselves.
Right. So let's start in the laboratory, our wind tunnel, so to speak.
Yeah, let's unpack this, because when we say clinical trial, the public immediately pictures researchers in white coats with clipboards.
They do.
But the formal definitions are incredibly precise. I think it's worth looking at how the International Conference on Harmonization, the ICH, actually defines it. It's not just giving people drugs to see what happens.
Far from it.
The ICH definition encompasses any investigation in human subjects intended to discover or verify the clinical, pharmacological, or pharmacodynamic effects of an investigational product.
Yes, and it doesn't stop there. The definition explicitly includes identifying any adverse reactions and studying the entire pharmacokinetic profile.
Right, like absorption, distribution, metabolism, excretion.
Exactly. All with the ultimate object of ascertaining safety and efficacy. It is a massive, sweeping mandate.
It essentially covers everything from giving a novel synthetic molecule to a human being for the very first time in a phase I trial.
Where you are really just looking at toxicity and maximum tolerated dose.
Exactly. All the way to the massive multi-center phase 3 and phase 4 trials that actually change international medical guidelines. But for our purposes today, as we look at testing causation under controlled conditions, we are focusing mostly on those late phase intervention trials.
And the crucial leap we need to make here is the jump from observational data to interventional data.
Oh, this is a big one.
If we connect this to the bigger picture, observational studies are the bedrock of epidemiology. They're incredibly useful for identifying patterns and suggesting associations. For example, a large cohort study might show that people who consume high amounts of dietary fiber have a lower incidence of colorectal cancer.
But observational studies are inherently plagued by confounding factors.
Precisely. The people who eat lots of fiber might also be the people who exercise more, smoke less, and have higher socioeconomic status, allowing for better general health care.
Right, you can statistically adjust for those confounders in your observational data, but you can never completely eliminate them. You can only suggest an association when you are just observing the world as it naturally exists.
But an intervention trial fundamentally changes the game.
Because it actually tests that association by actively manipulating the environment, You step in and change the exposure.
You take a group of people, you randomly assign half of them to receive a high-fiber supplement and the other half to receive a visually identical placebo, and then you watch what happens.
You intervene. Because diseases rarely have perfectly predictable paths. And perfect treatments, the kind of treatments that cure 100% of people with zero side effects, are essentially non-existent.
Most treatments are highly imperfect. They offer a nuanced balance of benefits and harms. Intervention trials are absolutely necessary to find that true, unbiased balance, minimizing those unknown confounding factors through rigorous, premeditated methodology.
Which brings up a fascinating distinction that public health professionals need to internalize: the difference between efficacy and effectiveness.
No, this is vital. I think people use those words interchangeably in normal conversation, but in trial design, they represent vastly different philosophies.
Right, an efficacy trial is essentially an explanatory trial.
Yeah.
It asks, does this intervention work under perfect, optimal, tightly controlled conditions?
It is the idealized version of reality. In an efficacy trial, you might select a very narrow, highly compliant demographic of patients who have no comorbidities. You monitor them constantly. If the protocol says they take the pill exactly at 8 in the morning with exactly 8 ounces of water and no one misses a dose.
Does the biological mechanism of the drug work?
Exactly. It answers a fundamental physiological question.
But the real world is not an idealized laboratory. Patients have complex lives. They have multiple overlapping diseases. They take other conflicting medications.
They forget to pick up their prescriptions.
And that is why we need effectiveness trials, which are often called pragmatic trials. A pragmatic trial asks, does this intervention actually work in the messy, chaotic real world?
Does it work when patients inevitably forget to take their pills on the weekend? Or when primary care doctors are rushed and prescribe it slightly incorrectly? Or when the patient's diet fluctuates wildly?
Effectiveness trials are designed to allow for non-adherence and real-world friction. They are much closer to predicting what will actually happen when the drug clears regulatory hurdles and hits the open market.
And generally, the effectiveness of a drug in a pragmatic trial is always lower than the efficacy of that same drug in an explanatory trial, simply because human behavior introduces so much variance.
Precisely. And understanding whether you are reading an explanatory efficacy trial or a pragmatic effectiveness trial completely changes how you interpret the results and apply them to your own clinical practice or public health policy.
Here's where it gets really interesting, though. Before we even design the perfect efficacy or effectiveness trial, before we recruit a single patient, we have to walk an incredibly narrow ethical tightrope.
Testing on humans carries an immense historical and moral weight. And the foundational concept that allows clinical trials to exist at all is called clinical equipoise.
Clinical equipoise is paramount. It is the ethical prerequisite for any randomized controlled trial. It means that a trial can only take place if there is genuine, documented uncertainty within the expert medical community about whether an experimental intervention is useful or whether it is better than the current standard of care.
Because if you don't have that uncertainty, if you already know for a fact that your new drug is vastly superior to the standard treatment, then randomizing a patient to the control arm means you are knowingly giving them a substandard, potentially harmful treatment.
And that violates the core oath of medicine.
Exactly. Now, individual doctors might have their own hunches. An investigator might passionately believe their new molecule is the cure.
But personal belief is not systemic knowledge. As long as the broader medical community is divided, as long as the existing data is genuinely inconclusive, clinical equipoise exists.
And that state of collective uncertainty is what justifies asking human participants to undergo potential hazards for the sake of generating new knowledge.
And that collective uncertainty ties directly into the concept of informed consent. But we have to look at informed consent not just as a legal liability waiver you sign in a waiting room and then immediately forget about.
Right. It's an ongoing, living process. And the true test of informed consent is what happens when things go wrong mid-trial.
That is a vital distinction. The HERS trial, the Heart and Estrogen Progestin Replacement Study, is a prime historical example of this. This was a massive trial investigating whether hormone replacement therapy could prevent secondary cardiovascular events in postmenopausal women who already had heart disease.
Okay, let's unpack this. What happened?
Well, during the trial, the researchers and the safety monitors noticed an unexpected, statistically significant increase in thromboembolic events. Basically, the women taking the active hormone therapy were developing dangerous blood clots in their legs and lungs at a higher rate than the placebo group.
That is a terrifying scenario for an investigator. Was that specific elevated risk of thromboembolism clearly stated on the original consent form that the women signed?
It wasn't stated as a known, highly probable, or significant risk simply because the investigators didn't anticipate it occurring at that magnitude. It was considered an uncommon possibility, but the actual data emerging from the trial was alarming.
So what do they do?
The trial wasn't halted immediately. They needed more data to confirm the trend, but the investigators recognized an absolute immediate ethical obligation to actively reinform the participants mid-study.
They couldn't just hide behind the original paperwork and say, well, you accepted the general risk of an experiment.
No. They proactively drafted letters. They informed the participants about the new emerging findings regarding the blood clots, and they even published a letter to the editor in major medical journals to alert the broader clinical community while the trial was still ongoing.
Informed consent means the participant must be kept informed of the risks as they evolve in real time. If the risk profile changes, the participant's consent must be reobtained under the new parameters.
Yes. So let's look at the other side of the equation. The comparison group. If you're testing a brilliant new drug, what exactly do you compare it against?
Placebos, the classic sugar pill, are the standard control group in the public imagination. But they aren't always ethical to use, are they?
This raises an important question about the fundamental tension between the rigid needs of a scientific study and the unyielding rights of the individual patient. If you are studying a minor condition for which there is no great treatment, say, the common cold placebo is perfectly fine.
But if there's a known, established, highly effective standard treatment for a serious or life-threatening disease, it is generally considered unethical to use a placebo control.
Exactly. You cannot withhold a life-saving or highly beneficial standard therapy like an established chemotherapy regimen for leukemia just to get a clean, zero baseline data set to compare your new experimental drug against.
Because the interests, safety, and well-being of the individual participant must always take precedence over the needs of the study or the desires of the scientific community. The strictures of a study protocol can never strip a clinician of their fundamental duty to do what is best for the patient sitting in front of them.
So in a scenario where a standard life-saving care exists, how do you design the trial?
You'd either test the new drug directly head-to-head against the standard therapy to see if it's better, or if you want to see if they work well together, you would give both groups the standard therapy and then add the new experimental drug to Group A and add a placebo to Group B.
That way, absolutely no one is being denied the baseline standard of care.
Precisely. It is an active control trial or an add-on trial. It preserves the scientific integrity of blinding and comparison without sacrificing the ethical mandate of patient care.
So what does this all mean when we sit down to actually define what we are studying? We've navigated the ethics. Now we need to define the architecture.
Let's look at defining the study question and outcomes. It's an ironclad rule of trial design that you live and die by your primary question. You can't just throw a bunch of variables at a wall and see what sticks.
A trial must have one single primary question, and it must be meticulously, rigidly defined in advance of the first patient being enrolled. This is non-negotiable.
Why is it so rigid?
Because that single primary question is what dictates the statistical power, the required sample size, and the entire financial and operational scope of the trial. You can certainly have secondary questions. Maybe you want to see if the drug that lowers heart attack risk also happens to improve kidney function. But the trial's success or failure is judged almost entirely on that primary question.
But I think where a lot of trial designers get trapped and where the history of medicine gets really dark is in the seductive nature of the outcomes themselves. Specifically, the danger of confusing a surrogate outcome with a true clinical outcome.
Okay, let's unpack this thoroughly. What exactly is a surrogate outcome, and why is it such a dangerous trap?
Well, a true clinical outcome is an event that directly and tangibly matters to the patient's life and well-being. Surviving a heart attack, avoiding a debilitating stroke, maintaining the ability to walk up. These are true clinical outcomes.
Right.
A surrogate outcome, on the other hand, is a biological marker, a lab value, or a physical measurement that we use as a substitute for that true clinical outcome.
It's the number on the chart. Blood pressure, cholesterol levels, bone mineral density, HbA1c, and diabetes. We assume that if we fix the number on the lab test, we naturally fix the patient.
We assume the biomarker is a perfect proxy for the disease process. And sometimes, to be fair, that assumption works brilliantly.
Blood pressure is a fantastic, highly validated surrogate for stroke and cardiovascular disease risk. Massive landmark trials in the 80s and 90s, like the SHEEP trial and the ALHAT trial, proved beyond a shadow of a doubt that if you use pharmacological interventions to lower chronically elevated blood pressure, you genuinely and proportionally reduce the occurrence of strokes and heart attacks.
In that case, the surrogate accurately and faithfully predicted the true clinical benefit.
But when a surrogate isn't perfectly validated, it can lead to catastrophic medical failures. And there is no better example of this than the Key ST disaster.
The cardiac arrhythmia suppression trial. This is one of the most chilling stories in cardiology, and it perfectly illustrates why we cannot rely solely on biological theory.
It is a profoundly sobering piece of medical history. In the 1980s, cardiologists knew that patients who had recently survived a myocardial infarction, a heart attack, and who also suffered from frequent premature ventricular contractions, or PVCs, were at a statistically much higher risk of sudden cardiac death.
The irregular heartbeats were a known, heavily documented risk factor.
So the biological rationale, the epidemiological reasoning seemed flawless. If the irregular heartbeats predict sudden death, then if we give these patients antiarrhythmic drugs to perfectly suppress the irregular heartbeats, we should logically prevent the sudden death.
The suppression of the arrhythmia was the surrogate outcome.
Exactly, and the pharmaceutical industry developed drugs, specifically incanide and flecainide, that were incredibly effective at doing exactly that. They worked beautifully at suppressing the arrhythmias on an ECG monitor. The surrogate outcome was a total, unmitigated success.
The electrical tracings looked perfect.
Based on that surrogate success, these drugs were widely prescribed. But the medical community eventually realized they needed a proper randomized controlled trial to prove the clinical outcome. That was the CAST trial.
And when they ran the CANIS-T trial and looked past the ECG monitors to see if the patients were actually living longer, what did they find?
They found something horrifying. The trial had to be halted prematurely. The patients randomized to take the antiarrhythmic drugs. The drugs that were successfully smoothing out their heartbeats were actually dying of sudden cardiac death at a significantly higher rate than the patients taking placebo.
Wow, by aggressively fixing the biomarker, they were actually killing the patients.
Yes. The human body is vastly more complex than a single electrical pathway. While the drugs suppressed the benign PVCs, they had other unforeseen proarrhythmic and toxic mechanisms that were ultimately fatal to a heart recovering from an infarction.
The intervention looked perfect on paper and perfect on a surrogate level, but it was deadly on a clinical level.
It perfectly proves why, unless a surrogate is flawlessly validated across multiple mechanisms, you cannot assume that changing a number on a chart equals saving a human life.
That is wild. It really reinforces why we have to test things all the way to the end of the line, to the true clinical outcome. And sometimes what we are testing isn't even a single drug molecule. We are testing a whole overarching philosophy of care.
The AFFIRM trial is a brilliant example of intervention versus strategy.
Yes, the AFFIRM trial is a classic example of pragmatic systems thinking. It looked at older patients with atrial fibrillation and an irregular, often rapid heart rate. For decades, the intuitive medical approach was that the heart is out of rhythm, so we must aggressively use powerful drugs or electrical cardioversion to force it back into a perfect, normal sinus rhythm.
That is the rhythm control strategy.
Right, but the alternative philosophy was rate control. Don't worry about the irregular rhythm, just use milder drugs to slow the heart rate down so it doesn't beat too fast, and give them blood thinners to prevent clots.
So AFFIRM didn't just test one specific pill against another. It tested these two entirely different medical philosophies: the aggressive pursuit of biological normalcy versus the pragmatic management of symptoms.
Exactly. Now, what's fascinating here is that if you only looked at the mechanistic intervention, the rhythm control group often failed. Despite all the aggressive drugs and shocks, only about 63% of the patients in the rhythm control arm were actually maintaining a normal sinus rhythm after 5 years.
So an observer might say, well, the intervention failed to do what it was supposed to do.
They might. But the trial wasn't designed just to look at the ECG. It successfully answered the broader, far more important strategy question. It proved that the strategy of simply controlling the rate was just as effective for long-term overall survival as the aggressive, side effect-heavy strategy of trying to control the rhythm.
In fact, rate control had fewer adverse effects and hospitalizations. They evaluated the clinical strategy, the actual management pathway, not just the biological mechanism.
Okay, so we've established our ethical boundaries. We know exactly what primary question we are asking. And we've ensured we are measuring a true clinical outcome, not a deceptive surrogate. Now, we actually have to build the physical architecture of the trial.
Let's look at trial designs.
The most basic, intuitive blueprint is the parallel design. You have Group A and you have Group B. They run parallel to each other. But even this simple design has hidden statistical math traps, especially if you get greedy and try to test too many things at once.
It does. The standard two-arm parallel design drug versus placebo or new drug versus old drug is the cleanest head-to-head comparison. But trial designers often think, well, since we are going to all the trouble and expense of recruiting thousands of patients, why don't we test drug A, drug B, drug C, and a placebo all at the same time?
It makes intuitive sense to maximize your resources. But mathematically, you face a severe statistical penalty called the alpha level division. Let's break this down for the listener. The alpha level is your threshold for statistical significance, usually set at 0.05. It means you accept a 5% chance that any positive result you find is just a random fluke, a false positive.
Right. If you run one comparison, drug A versus placebo, you have a 5% chance of a false positive. But every single time you add another comparison to that same trial, you are rolling the dice again. If you compare A versus placebo, B versus placebo, C versus placebo, and A versus B, suddenly you've rolled the dice so many times that the cumulative probability of finding a false positive purely by random luck skyrockets.
To maintain the overall integrity of the statistics, to ensure you don't publish a fluke, you have to strictly divide your alpha level.
Exactly. To account for multiple testing, you might have to use the Bonferroni correction or similar methods. So instead of needing a p-value of 0.05 to declare victory, you might suddenly need a p-value of 0.01. To hit that much stricter, tighter mathematical target, your trial needs immense statistical power.
And the only way to get that power is to drastically increase your sample size.
So adding arms to a parallel trial doesn't just make it a little more complex, it makes it exponentially more expensive, larger, and harder to complete.
Unless you use a factorial design.
Yeah.
This is one of my favorite structural workarounds in trial methodology. It is so elegant. Instead of just running parallel groups, you test multiple interventions simultaneously on the same population, exploiting the overlap.
You have a group getting drug A, a group getting drug B, a group getting both drug A and B, and a group getting neither, which is the true placebo.
It is a masterpiece of efficiency. Assuming the two drugs don't biologically interact with each other in a way that obscures their individual effects, you are essentially running two massive, fully powered trials for the price of one.
The textbook highlights several monumental successes of this design. The Physicians' Health Study is a classic. They randomized over 22,000 male physicians to receive either aspirin, beta-carotene, both, or neither.
They were able to simultaneously evaluate aspirin for cardiovascular disease and beta-carotene for cancer prevention within the exact same cohort.
And the ISIS-2 trial for heart attacks is another brilliant example. They tested aspirin and streptokinase, a clot-busting drug. They didn't just find out that aspirin works and streptokinase works. Because of the factorial design, the both group proved that the two drugs were additive.
Using them together was vastly superior to using either one alone. You couldn't have proven that cleanly with a simple parallel design.
Exactly. It maximizes the data generated from every single enrolled patient. But what if you don't have 22,000 physicians to enroll? What if you are studying a rare condition and you can only find 50 patients? In that case, you might turn to a crossover design.
This is a fascinating concept. In a crossover design, you, the listener, would act as your own control group. You are randomized to take the experimental drug for the first phase of the trial, say 6 weeks. Then you stop, you take a break. And then for the second phase, you cross over and take the placebo for 6 weeks.
Meanwhile, another patient does the exact reverse. Placebo first, then the drug.
The statistical advantage here is immense. Human beings are incredibly variable. We have different genetics, different diets, different baseline metabolisms. When you compare Group A to Group B, you need a huge sample size to wash out all that interpersonal variance.
But in a crossover trial, you are comparing your physiological response to the drug against your own physiological response to the placebo. The variance drops to almost zero. Therefore, you need a fraction of the sample size to achieve the same statistical power.
But there is a strict biological limitation on when you can use this. You can't use a crossover trial for a surgical intervention, obviously. You can't unremove an appendix. And you can't use it for a drug that cures the disease.
Right. The condition you are treating absolutely must be chronic, stable, and entirely reversible. Things like chronic neuropathic pain, stable asthma, or persistent eczema. If the drug permanently alters the disease pathway or if the patient is permanently cured during phase 1, there is no disease left to measure when they cross over to the placebo phase.
And that leads to the terror of the carryover effect. Even if the disease is chronic, what if the drug from phase 1 is still lingering in your system when you start taking the placebo in phase 2? Your placebo data is completely contaminated.
Which is why designers must build in a strict washout period between the phases. You calculate the pharmacokinetic half-life of the drug, and you make the patient wait multiple half-lives until the active molecule is entirely cleared from their bloodstream and tissues before they begin the second phase.
But even then, it is notoriously difficult to definitively prove that a prolonged biological or psychological carryover effect is entirely absent.
Let's shift to a design that is becoming incredibly common, especially in pharmaceutical development: equivalency and non-inferiority trials. This is a subtle but profound shift in the scientific question. You aren't trying to prove your expensive new drug is a miracle that beats the standard of care. You are just trying to prove that it's no worse than the current standard.
This often happens when a new drug might have similar efficacy, but offers a different advantage. Maybe it's a once-a-day pill instead of a 3-times-a-day pill, or it has a slightly milder side effect profile, or it's just cheaper to manufacture. You want to prove it's non-inferior.
But these trials are conceptually treacherous. They rely fundamentally on something called the constancy assumption.
Let's explore that. The constancy assumption means you are assuming that the active control drug, the established standard therapy you are comparing your new drug against, is still as effective today in your modern trial population as it was when it was originally tested and approved 20 years ago.
Yes. And if that assumption fails, the whole trial collapses. Imagine the standard therapy has gradually lost its edge. Maybe the bacterial pathogen has mutated and developed slight resistance, or maybe the baseline health of the population has changed.
If the standard therapy is actually performing poorly in your current trial, and you successfully prove your new experimental drug is no worse than the standard drug, you might have just spent $50 million proving that your new drug is equally ineffective.
That is a phenomenon sometimes called biocreep, where slightly inferior drugs are approved as non-inferior to the standard, and then that slightly inferior drug becomes the new standard for the next trial, leading to a downward spiral of efficacy. And there is another massive blind spot with non-inferiority trials. They actually reward sloppy science.
It is a dark paradox of trial execution. In a standard superiority trial, where you're trying to prove A is better than B, sloppiness hurts you. If your investigators are careless, if patients miss doses, if the data collection is noisy and full of errors, all that static obscures the signal. The two groups will look identical, and your trial will fail to show a difference.
Sloppiness drives the result toward the null hypothesis.
Exactly. But in a non-inferiority trial, your entire goal is to prove the two groups are the same. So if you run a sloppy trial and patients don't take the medicine and the data is a mess, the statistical noise will mask any real differences between the drugs.
The two groups will look identical, and the sloppy investigator can triumphantly declare, "Look, we couldn't find a difference. Our new drug is perfectly non-inferior."
That is deeply concerning from a regulatory standpoint. It means the FDA or the EMA has to scrutinize the operational execution of a non-inferiority trial even more fiercely than a superiority trial.
Which brings us perfectly into the execution phase. We have our blueprints. Now, let's talk about the raw mechanics of running the experiment. Let's look at the math of human behavior: sample size, randomization, and the eternal struggle of adherence. We have to start with what is arguably the single greatest methodological innovation in the history of modern clinical medicine: randomization.
It's elegant in its simplicity, but staggering in its power. When you take a cohort of 1,000 patients and randomly assign them to either the treatment group or the control group, you aren't just deciding who gets the pill. You are doing something almost magical to the data. You are distributing confounding factors evenly across both sides of the ledger.
It is the ultimate shield against bias. And the beauty of randomization is that it doesn't just balance the known confounders, the things we can measure, like age, weight, baseline blood pressure, or smoking status. If the sample size is sufficiently large, the random coin flip ensures that the unknown confounders are also washed out evenly.
The genetic quirks we haven't mapped yet, the subtle environmental exposures, the dietary trace elements. If the groups are large enough, pure probability dictates that both Group A and Group B will have an equal share of those hidden variables.
Therefore, if Group A has a wildly better clinical outcome, you can confidently attribute it to the one single thing that is different: your intervention. It transforms correlation into tight causal inference.
But as any trial designer will tell you, you can't just literally flip a coin for every single patient as they walk through the door. Pure chance is clumpy. If you just flip a coin for the first 20 people enrolled, you might end up with 16 in Group A and 4 in Group B just by a fluke of probability, and that completely wrecks your statistical power.
So we don't leave it to a simple coin toss. We engineer the randomness. Trial designers use fixed, blocked, and stratified randomization. Blocked randomization is particularly clever. It ensures that the trial stays perfectly balanced as it progresses.
Yes, in blocked randomization, you might set a block size of, say, 4. Within every block of 4 patients, the computer guarantees that 2 will get treatment and 2 will get placebo. So even if the trial is halted early after only 40 patients, you know you have exactly 20 in each arm.
But there is a catch. If the clinical investigator figuring out the assignments knows the block size is 4, and the first 3 patients they enrolled were randomized to A, B, and A, the investigator suddenly knows with absolute mathematical certainty that the next patient must be assigned to B.
And that completely breaks the integrity of the trial. If the investigator knows the next patient is destined for the placebo group, they might subconsciously or consciously decide not to enroll a particularly sick patient who they feel really needs the active drug. That introduces profound selection bias before the trial even begins.
Which is why we need to talk about allocation concealment. This is the unsung hero of trial integrity. It is different from blinding. Blinding keeps everyone in the dark after the patient is enrolled. Allocation concealment keeps the investigator in the dark before the patient is enrolled.
Exactly. To maintain allocation concealment with blocked randomization, the statisticians will randomly vary the block sizes. One block might be 4, the next might be 6, the next might be 8. The investigator never knows the pattern, so they can never predict the next assignment.
In the old days, this was done with sequentially numbered, opaque, sealed envelopes. You couldn't hold it up to the light to see what was inside. Today, it's almost entirely handled by centralized, automated computer systems. The doctor clicks enroll, and the server in another country spits back a randomization code.
And then, once they are enrolled and the allocation is concealed, we want to implement blinding, or masking, to prevent observation bias. Single blind means the patient doesn't know what they are getting. Double blind means neither the patient nor the doctor evaluating them knows. Triple blind even keeps the statisticians in the dark until the very end.
Double blinding is the gold standard, particularly when your clinical outcome is somewhat subjective, like assessing a patient's pain level or psychiatric improvement. If the doctor knows the patient is on the miracle drug, they might interpret a minor improvement as a major breakthrough. Blinding prevents that enthusiasm from corrupting the data.
But it's not always possible. As we discussed earlier, you cannot double blind a surgical trial. The surgeon obviously knows if they performed a bypass or not. In those cases, you have to rely on blinding the independent adjudicators who review the final data.
Okay, so we've got our perfectly concealed, beautifully blinded, stratified, and randomized groups. The statistical architecture is flawless. And then human beings actually enter the trial.
And human behavior ruins clean math. Let's talk about adherence and the sheer terror of Lochin's correction factor.
This is where pristine statistical theory collides violently with reality. Over the course of a 3-year trial, human nature takes over. You will inevitably have dropouts. These are people randomly assigned to the active intervention group who, for whatever reason, just stop taking the medication. Maybe the side effects bother them, maybe they lose their insurance, maybe they just get tired of swallowing pills.
And on the flip side, you have drop-ins. These are people randomly assigned to the placebo control group who get nervous about their health, do some reading on the internet, and secretly start taking the active intervention, maybe by getting a parallel prescription from a different doctor who isn't affiliated with the trial.
Both of these behaviors are disastrous for the trial's math. They systematically narrow the measurable difference between the two groups. The intervention group gets artificially less healthy because a chunk of them stopped taking the drug, and the control group gets artificially healthier because a chunk of them started taking it. The signal-to-noise ratio plummets.
And the statistical penalty for this non-adherence is brutal. Lochin's correction factor is the mathematical formula used to calculate exactly how much you need to increase your sample size to maintain your desired statistical power in the face of this non-adherence. And it's not a linear penalty. The factor is squared.
That is the killer detail. Because the non-adherence rates are essentially squared in the denominator of the sample size equation, the required sample size balloons exponentially. If your combined non-adherence rate dropouts plus drop-ins reaches just 20%, you don't just need 20% more patients. You might have to increase your total sample size by 50% or more to mathematically overcome that noise. That means millions of dollars in added costs and years of delay.
So how do brilliant trial designers combat that up front? How do you weed out the non-adherers before they can destroy your math?
You use a run-in period. The Physician's Health Study, which we mentioned earlier, used this tactic flawlessly. Before they officially randomized anyone, they put all the potential willing participants into a run-in phase. They gave everyone a blister pack of the active medication and told them to take it for a few weeks.
It's essentially an audition.
Exactly. After the run-in period, the investigators checked the blister packs. They looked at who actually took the pills reliably and who complained about minor side effects. Only the people who proved through their behavior that they could stick to the rigid regimen were officially enrolled, randomized, and counted in the final data.
It's incredibly smart.
Sure.
They filtered out the non-adherers before Latchin's correction factor could punish them, but it does come with a philosophical trade-off. It slightly damages the external validity or generalizability of the results, because your trial data now only perfectly represents a highly compliant, incredibly responsible subset of patients. It might overstate the drug's effectiveness in the chaotic real world where patients aren't pre-screened for perfect behavior.
It's a classic trade-off between internal validity, making sure the math is sound, and external validity, making sure the results apply to the general public.
Let's move into the phase where the data actually starts rolling in. We need to talk about analysis, ethics, and the data dredging trap. Once a massive multi-center trial is running, who actually has their hands on the emergency brakes? The blinded investigators can't see the data. The sponsors shouldn't see it.
That responsibility falls to the DSMB, the Data and Safety Monitoring Board. This is an independent, external committee of clinical experts, ethicists, and biostatisticians. They are the only people allowed to routinely look at the unblinded, real-time data while the trial is ongoing.
And they were looking for three specific things: overwhelming benefit, clear harm, or absolute futility.
Correct. The ethical mandate of the DSMB is profound. If, halfway through the trial, the unblinded data shows that the new experimental drug is miraculously curing a deadly disease, it becomes profoundly unethical to keep the control group on a placebo. The DSMB will halt the trial early for overwhelming benefit and offer the new drug to everyone. Conversely, if the new drug is unexpectedly causing severe liver failure, they must instantly halt the trial for clear harm to protect the participants.
And futility means that even if the trial runs perfectly to the very end, there's mathematically no way the drug will show a benefit, so there's no point in continuing to expose people to an experimental compound.
But hold on, didn't we just discuss the alpha level penalty? If the DSMB keeps peeking at the unblinded data every 6 months, aren't they running multiple comparisons and massively inflating the risk of a false positive?
Yes, every time they peak, they spend a little bit of the trial's alpha. To prevent this from ruining the final statistical integrity, the DSMB uses incredibly strict mathematical algorithms called stopping boundaries, like the O'Brien-Fleming boundaries or the Hay-Little-Pato boundaries. How do those boundaries work in practice?
Essentially, they set the bar for early termination astronomically high. If the DSMB looks at the data at the 25% mark, they won't stop the trial for a standard p-value of 0.05. To stop the trial that early, the drug has to be performing incredibly well, maybe hitting a p-value of 0.0001. The boundary is very conservative early on. As the trial progresses toward completion, the statistical boundary gradually relaxes, funneling down until it reaches the standard 0.05 at the very final analysis. It ensures that trials are only halted early for truly undeniable, massive effects, preventing false positives from prematurely changing medical practice.
If we connect this meticulous oversight to the bigger picture of final analysis, we have to talk about what I think is the most counterintuitive, brain-bending concept in all of public health statistics: intention to treat, or ITT analysis. The golden rule of ITT is you must analyze every single participant in the group they were originally assigned to, regardless of what happened afterward. Even if they completely stopped taking the drug, even if they took the wrong drug, even if they dropped out, their data stays in their original assigned column.
It is incredibly difficult for many clinicians to accept at first glance. A practicing doctor looks at that rule and says, that's absurd. If the patient threw the pills in the trash and never swallowed a single dose, how can we possibly use their health outcome to judge if the biological mechanism of the drug works?
Right. The instinct is to clean up the data, to say, let's only analyze the people who actually adhered to the protocol. That's called a per-protocol analysis. But the history of trial designs shows why per-protocol analysis is incredibly dangerous and why intention to treat is absolutely essential. Let's unpack the famous coronary drug project to prove this.
The Coronary Drug Project from the 1970s is the textbook case study for ITT. They were testing a lipid-lowering drug called clofibrate to see if it prevented mortality in men who had suffered heart attacks. At the end of the trial, 5-year mortality in the active clofibrate group was 20%. Mortality in the placebo group was 21%. Statistically, there was no meaningful difference. The drug appeared to be a failure.
But then, the investigators decided to dig deeper. They decided to do a per-protocol analysis on the active drug group. They separated the people who actually adhered to the regimen and took the clofibrate faithfully from the people who dropped out and didn't take it.
And they found exactly what they hoped to find. The good adherers who took the clofibrate had a 5-year mortality rate of only 15%. The poor adherers who didn't take it had a mortality rate of nearly 25%.
So a doctor looking at that specific cut of data would say, aha, the drug works perfectly. The overall trial only failed because lazy patients didn't take their medicine. If you take the pill, you live.
That is exactly what they would say. But the investigators in the Coronary Drug Project were brilliant. They decided to run the exact same adherence analysis on the placebo group. They separated the people who faithfully took their useless sugar pill every single day from the people who forgot to take their useless sugar pill.
And this is the punchline that shook the epidemiological world. What did they find?
They found the exact same survival pattern in the placebo group. The people who faithfully, religiously took a useless placebo had a mortality rate of 15%. The people who forgot to take the placebo had a mortality rate of 28%.
Wait, taking a pharmacologically inert placebo pill perfectly made them significantly healthier. How is that possible?
It wasn't the pill. What this brilliant analysis proved is the existence of the healthy adherer effect. Adherence itself is a powerful marker for generalized positive health behavior. Think about it. A person who is organized and conscientious enough to remember to take a study pill exactly at 8 in the morning every single day for 5 years, what else are they doing?
They are probably eating a meticulously healthy diet. They are exercising regularly, they have a stable home life, they aren't smoking, and they are visiting their primary care doctor for every minor symptom.
Exactly. They are inherently healthier people due to a massive cluster of positive, unmeasured, confounding factors. The people who forget to take the pills are often the ones with chaotic lives, higher stress, poor diets, and poorer baseline health. So if you do a per-protocol analysis, if you remove the non-adherers from your active drug group, you aren't just removing bad data. You are systematically filtering out all the bad health behavior people. You are artificially creating a superhuman, concentrated subgroup of highly compliant, naturally healthy people.
Oh, and then if you compare that artificially concentrated healthy group against the entire placebo group, which still contains all of its chaotic, non-adherent people, your new drug will look like an absolute miracle. But the drug didn't save them. You just mathematically rigged the demographics.
Yes, you completely destroyed the randomization that you worked so hard to achieve at the beginning of the trial. Intention to treat analysis forces you to keep everyone exactly where they were randomized, warts and all. It is the only way to protect the statistical balance of confounders. It evaluates the strategy of prescribing the drug in the real world, where non-adherence is a fact of life.
That is mind-blowing. It shows how incredibly fragile data can be if you analyze it with a bias. Which leads us seamlessly into the final trap of the wind tunnel, the danger of subgroup analysis. If a massive trial fails to show an overall benefit, the pharmaceutical sponsor or the investigator will feel an overwhelming, almost physical temptation to chop up the data to salvage something. Well, the drug didn't work for the general population, but what if we only look at the data for left-handed men over 60 who have a history of mild asthma?
That is called data dredging, or p-hacking. And it is a mathematical fallacy. If you slice a large, complex data set into enough distinct subgroups, pure statistical variance guarantees that you will eventually find a specific group where the drug appears to work beautifully, entirely by chance. Remember the alpha level we discussed. If you run 20 different subgroup analyses, you are virtually guaranteed to find at least one false positive.
And to prove how absurd this is, we have to look at the ultimate cautionary tale in epidemiology, the ISIS-2 trial again. The principal investigators of ISIS-2, including Richard Petto, were exhausted by clinicians constantly demanding subgroup analyses. They wanted to mathematically prove that slicing data post hoc is essentially just drawing shapes in the clouds. So they deliberately sliced their pristine, perfectly executed heart attack data by the participants' astrological signs.
It is one of the greatest pedagogical jokes in medical history. They used real, rigorous data to mathematically prove that aspirin is a life-saving miracle drug for patients having a myocardial infarction, unless you happen to be born under the star sign of Gemini or Libra. For Geminis and Libras, the data showed that aspirin was apparently completely useless.
It's the perfect mic drop. I mean, imagine a cardiologist asking a patient, clutching their chest, wait, were you born in June? Because if you're a Gemini, the guidelines say I shouldn't give you this aspirin. It proves beyond any doubt that unless you define your specific subgroups rigidly and biologically in advance of the trial, finding a correlation later is literally statistical astrology.
Precisely. You cannot use the same data to generate a hypothesis and then instantly prove that hypothesis. You must take that new hypothesis and test it again in a fresh trial.
Which brings us to a massive pivot point in our conceptual journey today. We have spent all this time in the controlled, rigorous wind tunnel of intervention trials. We have meticulously proven that a specific biological intervention works, and we have mathematically guarded against bias, adherence drop-offs, and data dredging. Now, we leave the lab. How do we take that proven, powerful intervention and deploy an early warning radar across all of society to find the exact people who desperately need it?
We shift our focus to population screening, and this requires a complete shift in our ethical and operational frameworks.
Let's start by aggressively redefining the word screening, because clinicians and the general public use that word incorrectly all the time.
They do. In the rigorous realm of public health, true screening means systematically, proactively inviting a defined population of asymptomatic, apparently perfectly healthy people to undergo a diagnostic test. It is an active, organized, programmatic outreach. It is not waiting in a clinic for people to get sick and come to you. It is the government or the healthcare system actively reaching out to healthy communities.
And how is that fundamentally different from what doctors do every day, which is case finding?
Case finding, which is often called opportunistic testing, happens within a clinical encounter. If you go to your general practitioner because you sprained your ankle and while you were sitting on the exam table, the doctor decides to wrap a cuff around your arm and check your blood pressure, that is opportunistic testing. It is incredibly useful and it saves lives, but it is an individual clinical decision. It is not population screening. Screening is a coordinated, massive public health system requiring IT infrastructure, quality assurance boards, and standardized follow-up pathways.
And because true screening targets millions of people who feel perfectly fine, it introduces what ethicists call the fundamental paradox of screening. It fundamentally inverts the traditional doctor-patient dynamic. Unlike a hospital treatment where a terrified sick person comes to you begging for an intervention, a screening program invites perfectly healthy, oblivious people to undergo medical procedures.
This is the absolute crux of screening ethics. When a patient is already suffering from advanced cancer, they are incredibly willing to accept the severe, toxic side effects of chemotherapy or the risks of a major surgery because the alternative, letting the disease progress, is worse. The risk-benefit ratio leans heavily toward intervention. But in a screening program, the healthcare system is the one initiating contact. We are sending a letter to their house. And by sending that letter, we are making an implicit systemic promise that participating in this test will ultimately benefit them.
Therefore, the threshold for harm is virtually zero. Any harm caused by the screening program, whether it's a psychological terror of a false alarm, a physical complication from an unnecessary biopsy, or the cumulative radiation from yearly scans, is incredibly difficult to accept or justify. Because you inflicted that harm, that anxiety, on someone who woke up that morning feeling perfectly fine and healthy.
Exactly. We are violating their healthy ignorance. Because of this massive ethical burden, public health officials cannot simply screen for every disease we have a test for. We need incredibly strict rules to govern when a screening program is actually deployed.
And those rules were laid out beautifully in 1968. The Wilson and Youngner criteria are basically the 10 Commandments of public health screening. They were later expanded upon by groups like the UK National Screening Committee, but the core tenets remain the same.
Let's walk through the major ones. First, the condition being screened for must be an important health problem. You don't build a national infrastructure to screen for something trivial. Second, the natural history of the disease must be adequately understood. You have to know how it progresses from a latent silent phase to a clinical phase. If the disease acts unpredictably, screening is useless.
Third, there must be a recognizable latent or early symptomatic stage. You need a window of time where the disease is there, but not causing obvious symptoms yet. And fourth, critically, there must be an accepted, effective treatment available for patients with recognized disease.
That last point cannot be overstated. There is zero public health value and immense ethical harm in systematically screening a population to diagnose a devastating disease for which you have absolutely no cure or mitigating treatment. You are simply giving people a death sentence years earlier than they would have otherwise known, vastly increasing their years of suffering and anxiety without altering their final outcome.
Which brings us to the fifth major criterion. There must be a suitable test or examination that is highly validated and acceptable to the population. Let's zoom in on the nuance of the test itself. We need to talk about sensitivity, specificity, and the most important metric of all, positive predictive value, or PPV. I think the classic clinical misperception is that sensitivity is the only thing that matters. The rallying cry is always, we can't miss a single case, make the test more sensitive.
It is a very common and very dangerous clinician mindset when applied to populations. Let's define the terms conceptually. Sensitivity is the ability of the test to correctly identify everyone who truly has the disease. If you have a room of 100 genuinely sick people and your test rings the alarm for 99 of them, you have 99% sensitivity. The test missed one person, a false negative. Clinicians love high sensitivity because the worst thing in individual medicine is sending a sick patient home undiagnosed.
But in population screening, where you are testing millions of healthy people, specificity actually reigns supreme. Specificity is the ability of the test to correctly identify everyone who does not have the disease. It is the ability to stay quiet when nothing is wrong.
Right. And here's why specificity is the absolute king of public health screening. We have to look at how these metrics interact with the real world using Bayes' theorem, which gives us the positive predictive value. PPV answers the only question the patient actually cares about. My test just rang positive. What are the actual chances that I have the disease?
Let's do the math on this because it is staggering. Let's say we have a disease with a 0.1% prevalence in the general population. That's 1 in 1,000 people.
Okay, 1 in 1,000. That is our baseline prevalence. Now, a biotech company develops a seemingly incredible screening test. It has 95% sensitivity and 95% specificity. In a lab setting, that sounds like an A+ grade. We roll this national screening program out to 100,000 completely asymptomatic, healthy-feeling people.
Based on the 0.1% prevalence, out of those 100,000 people, exactly 100 of them actually have the hidden disease.
Correct. So we run the test on everyone. Our test is 95% sensitive. So out of the 100 truly sick people, the test correctly finds 95 of them. Fantastic. We saved 95 lives.
But what about the other 99,900 people who are completely healthy?
That is where the trap snaps shut. Our test is 95% specific, which means it correctly identifies 95% of the healthy people as healthy. But that also means it has a 5% false positive rate. It will ring the alarm on 5% of healthy people. So we apply that 5% false positive rate to the 99,900 perfectly healthy people in our cohort. The test generates approximately 5,000 false positive results.
Oh, wow. So at the end of the screening campaign, your call center has a list of 5,095 people who got a positive result. 95 of them are true positives, hidden in an absolute ocean of 5,000 false positives.
Exactly. When you calculate the positive predictive value, the true positives divided by all the positives, it is less than 2%. If a patient gets a terrifying phone call saying, your cancer screening test came back positive, there is a 98% chance they're completely, totally healthy.
But we just caused immense, life-altering psychological anxiety for 5,000 families. And we now have to send all 5,000 of those healthy people for invasive follow-up diagnostics, maybe a tissue biopsy or an expensive MRI. Those follow-ups carry their own physical risks of infection or bleeding, and they cost the healthcare system millions of dollars, completely clogging the diagnostic pipeline for people who actually have symptoms.
That is the iron law of screening. Prevalence drives PPV. If a disease is rare in the population you are testing, even a mathematically brilliant test will bury your healthcare system in false positives. The lower the prevalence, the more crucial specificity becomes.
Which is why you have to tailor the screening program to the population. You can't just blindly roll it out everywhere. A brilliant example of recognizing this dynamic is the thalassemia screening protocol in the UK.
Yes, screening for beta thalassemia, which is a genetic blood disorder. The primary screening metric is a routine blood test looking at mean cell hemoglobin, or MCH. They set a specific MCH cutoff level to flag potential carriers. In London, where the population is highly diverse and the prevalence of the genetic trait is relatively high, that specific cutoff level worked reasonably well. The PPV was manageable because the disease was common enough in that demographic.
But when they took that exact same blood test with the exact same MCH cutoff and rolled it out to low prevalence, predominantly white areas in other parts of the country, the false positives skyrocketed, just like in our math example. The regional healthcare systems were suddenly overwhelmed with unnecessary, expensive follow-up DNA testing on completely healthy people.
So how did public health officials fix it? They couldn't magically change the biological sensitivity of the MCH blood test itself. It was a fixed scientific reality.
They changed the system. They added a simple 2-minute questionnaire about the patient's family origins. Because the thalassemia trait is highly linked to specific ethnic backgrounds, particularly Mediterranean, Middle Eastern, and South Asian ancestries, they realized they could use epidemiology to boost the test. By using the MCH blood test in combination with the family origin questionnaire, they drastically increased the overall specificity of the screening protocol.
It was a stroke of logistical genius. If you were in a low prevalence area, but your blood test was slightly flagged, they wouldn't automatically send you for expensive DNA testing unless your family origin questionnaire also indicated a higher risk. That simple, zero-cost systemic tweak reduced unnecessary follow-up testing by an astonishing 96%. It saved immense healthcare resources, unclogged the labs, and spared thousands of families from needless anxiety.
That is the pinnacle of systems thinking right there, tweaking the operational protocol to save the biological system. But even when a screening program runs smoothly, we have to be incredibly skeptical of the data it produces. Sometimes the success data we get from a screening program is just a statistical illusion. We need to explore the hidden harms and costs of screening. Let's talk about the two massive conceptual traps that make screening look much better than it actually is: lead time bias and length time bias.
These are essential concepts for any public health professional to master, particularly when evaluating cancer screening. Let's start with lead time bias. This occurs when a screening test successfully advances the time of diagnosis. It catches the disease earlier, but it does not actually change the ultimate clinical course of the disease or the patient's time of death.
Let me build an analogy for this. Imagine a man who develops a hidden tumor at age 60. If he is never screened, he will eventually notice a physical lump or start feeling pain at age 65. He goes to the doctor, he is diagnosed with advanced cancer at 65, and despite treatment, he tragically dies of the disease at age 67. His measured survival time from the point of diagnosis is 2 years.
Correct. That is the natural, unscreened clinical pathway. Now imagine we enroll that exact same man in a brand new, highly aggressive screening program. He gets screened at age 61. The high-tech scan catches the tiny asymptomatic tumor 4 years earlier than he would have naturally noticed it. He is diagnosed at 61. He receives years of intensive treatment, but the biological nature of this specific cancer is relentless, and he still ultimately dies at age 67.
But look at what happens to the statistics. The administrators running the screening program will look at his file and claim a massive victory. They will say, look, without screening, survival time was only 2 years. But our screening program increased his survival time from diagnosis to 6 years. We tripled his survival time.
Exactly. The statistics look absolutely amazing in the press release. Screening drastically improves 5-year survival rates. But in objective reality, the screening program didn't add a single day to his actual lifespan. He died at the exact same age. All the screening program did was give him 4 extra years of knowing he had a terminal disease, saddling him with 4 extra years of severe psychological distress and the toxic, debilitating side effects of early chemotherapy. That is the illusion of lead time bias. It stretches the tape measure of survival without actually moving the finish line.
That is deeply sobering. And what about length time bias?
Length time bias is a slightly different illusion, and it has to do with the aggressive nature of different tumors. Not all cancers are the same. Imagine a population with 2 types of tumors. Some tumors are like aggressive cheetahs. They grow incredibly fast, they spread quickly, and they kill the patient in a matter of months. Other tumors are like slow-moving turtles. They grow very slowly, they are relatively benign, and they might sit in the body for decades without ever causing a symptom or threatening the patient's life.
Okay, cheetahs and turtles.
Now, imagine you set up a screening program where you scan the population once every 2 years. Which animal are you statistically more likely to catch in your trap? The slow-moving turtles are in the body for a very long time, patiently waiting to be found. Because their latent phase is so long, your biennial screening program is highly likely to intercept them. But the fast-growing cheetahs, they pop up out of nowhere, grow rapidly, and kill the patient in the long interval between your yearly screenings. They become what we call interval cancers.
Ah, So the screening program is inherently structurally biased toward only catching the slow, relatively benign cancers.
Right. And because those slow-growing turtle cancers naturally have very high survival rates anyway, some of them would never have killed the patient even if left completely alone, the screening program takes all the credit for saving them. It creates a massive statistical illusion. The program looks like it has an incredible survival rate when in reality it is simply disproportionately diagnosing the least dangerous cancers while completely missing the deadly ones.
And when you start aggressively diagnosing and treating all those slow-moving turtles that would never have bothered the patient, you plunge right into the massive economics and opportunity costs of overdiagnosis. A screening program isn't just a matter of buying the initial testing kits at the ultrasound machines. It is a massive, sprawling industrial complex.
The economic modeling for screening is notoriously flawed. Planners often severely underestimate the downstream systemic costs. They budget for the ultrasound machine and the technician's hourly wage. But they fail to calculate the massive systemic costs of organizing and mailing tens of thousands of invitation letters, maintaining massive secure IT databases to track who showed up and who didn't, funding the complex quality assurance boards to monitor the labs, and critically paying for the surgical suites, the anesthesiologists, and the intensive care beds required to treat all the thousands of people who test positive.
The abdominal aortic aneurysm, or AAA, screening program is a perfect example of this financial blind spot.
Yes. When AAA screening was evaluated, the initial cost models looked acceptable. But when implemented, not only were the systemic infrastructure costs vastly higher than predicted, but the real-world prevalence of the disease had actually fallen due to population-wide reductions in smoking. Because the prevalence was much lower than the outdated mathematical models predicted, they had to screen vastly more men to find a single true case. The cost per case found became astronomically higher than planned, diverting precious healthcare funding away from other, potentially more impactful public health interventions.
Which leads us to one of the most fascinating and frankly disturbing concepts in this entire deep dive. It explains why, even when a screening program is economically disastrous and medically harmful, it is almost politically impossible to shut it down. It is called the popularity paradox, coined by public health experts Raffel and Gray.
The popularity paradox is a dark, brilliant irony of public health psychology. Let's imagine a hypothetical screening program that is objectively terrible. It is highly inaccurate, it causes massive overdiagnosis, and it finds hundreds of tiny, benign cellular abnormalities, those turtles that would never, ever have progressed to cause a symptom in the patient's natural lifetime.
But the program labels those benign abnormalities as early-stage cancer, and the medical system aggressively treats them with surgery and radiation.
Yes. Statistically, epidemiologically, that is a terrible, actively harmful public health program. It is subjecting healthy people to unnecessary mutilation. But socially and politically, what happens? You now have hundreds, maybe thousands of people who were told they had cancer, received treatment, and are now technically cured. They family passionately believe that this specific screening program saved their lives.
They become fierce, incredibly vocal advocates. They start charities, they run marathons for the cause, they lobby politicians to mandate expanding the program to younger and younger ages.
Exactly. And the paradox is this. The more a screening program overdiagnoses and harms people, the more wildly popular it becomes.
Wow.
Because every single time it overdiagnoses a harmless abnormality, it mints a new, highly motivated survivor who will publicly defend the program to the death. Meanwhile, a truly perfect screening program that only identifies aggressive, deadly cancers will inevitably have a lower overall survival rate and therefore generate fewer vocal advocates.
That is absolutely chilling. The worse the program is, the louder its defenders are. And that perfectly explains the immense institutional inertia we see historically.
Yeah.
Once a screening program is turned on, it's nearly impossible to turn it off.
The momentum is practically unstoppable. We can look at two striking historical examples. In Japan, the government instituted a national neuroblastoma screening program for infants in 1985, testing their urine at 6 months of age. It was incredibly popular with parents. But years later, rigorous international evidence, including massive trials from North America and Europe, conclusively proved that screening for neuroblastoma at that age didn't reduce mortality by a single percentage point.
Why not?
Because it was the ultimate example of overdiagnosing the turtles. The screening was catching neuroblastomas that were biologically destined to spontaneously regress and disappear on their own. The program was just overdiagnosing benign tumors and subjecting perfectly healthy infants to completely unnecessary, dangerous abdominal surgeries and chemotherapy. Yet, even with absolute, undeniable proof of massive harm and zero benefit, the program was so entrenched and popular that it took a massive, agonizing, highly coordinated government and academic effort to finally halt the screening in 2004.
And the Danish TB stations are an even starker example of bureaucratic inertia.
Yes, Denmark established a fantastic network of mobile tuberculosis X-ray screening stations in the mid-20th century. It was vital work at the time. But due to antibiotics and better living conditions, TB was essentially eradicated as a major public health threat in the country. Yet the Danish government kept those X-ray screening stations running for roughly 20 years after the disease was gone.
They were just maintaining the bureaucratic status quo.
Exactly. They were systematically X-raying hundreds of thousands of healthy citizens, subjecting the entire population to cumulative doses of ionizing radiation, which carries its own small but real risk of inducing cancer, in order to look for a disease that mathematically wasn't there anymore. It highlights that public health programs can easily become self-justifying industries if they aren't constantly reevaluated against current epidemiology.
As we move into our final area, the ethics and life stages of screening, we see how this institutional inertia interacts disastrously with societal stigma and ignorance. We have to talk about the U.S. Sickle Cell Act of 1970. This is a profound lesson in how good scientific intentions can result in sociological catastrophes if the public isn't educated.
It was a classic, tragic public health failure. The political intention behind the act was noble: to identify carriers of the sickle cell trait in the African American population to provide genetic counseling. But they rolled out the widespread screening test without building any of the necessary social, educational, or psychological infrastructure to handle the complex results.
Specifically, they completely failed to educate the public on the fundamental, critical difference between being a healthy genetic carrier of the trait and actually having the severe, debilitating sickle cell disease.
And panic ensued. Tens of thousands of people got their screening results back in the mail saying they were positive for the sickle cell trait. Because of the lack of education, perfectly healthy carriers were suddenly severely stigmatized by their own communities and by institutions.
They were viewed as being diseased.
Yes. Healthy carriers were denied health insurance or charged exorbitant premiums. Some even lost their jobs or were denied employment, particularly in physical labor or the military, because employers fundamentally misunderstood the science and thought these healthy carriers were at risk of sudden physical collapse.
It proves that biological information is not inherently benign. When the state initiates a test, it must manage the societal fallout of the answer. In genetic screening, the dark, historical shadow of eugenics is always lingering. We have to tread incredibly carefully when we start labeling perfectly healthy citizens based on their DNA.
Which brings us to how we cautiously apply these lessons across the life stages today. Let's do a rapid-fire overview of where public health screening currently stands. Starting at the very beginning of life, antenatal and newborn screening.
Newborn blood spot screening, the heel prick test, is practically universal in developed healthcare systems now. We look for metabolic conditions like phenylketonuria and genetic conditions like cystic fibrosis and sickle cell disease. But even here, there's an ongoing ethical debate over revealing carrier status.
It is a profound debate. When we test a baby's DNA to see if they have cystic fibrosis, the exact same genetic test inadvertently tells the laboratory if the baby is a healthy carrier of the recessive gene. The ethical dilemma is, should the state tell the parents that their healthy baby is a carrier?
Because the infant obviously cannot consent to having their long-term reproductive genetic information sequenced and handed over to their parents.
Exactly. Some ethicists argue it violates the child's future right to an open future and genetic privacy. However, the pragmatic public health view, supported by bodies like the UK Human Genetics Commission, decided that generally carrier status should be reported. The rationale is that it provides crucial reproductive information for the parents' future pregnancies, ensuring the family understands their overall genetic risks. But it remains a delicate balance of competing rights.
Moving into adulthood, the landscape is dominated by cancer screening, which is incredibly emotive and heavily debated. We've got the breast cancer debates.
Mammography screening is fiercely, constantly debated in the epidemiological literature. The Forrest Report laid the original groundwork for the UK's breast screening program, but the parameters are always under fire. There's constant arguing over the age intervals. Should we start screening women at age 40? Or wait until 50 when the incidence rate is higher and the breast tissue is less dense, making mammograms easier to read? Should we screen every single year or every 3 years? The risk of overdiagnosis, false positives leading to unnecessary biopsies, and the cumulative radiation exposure must be constantly mathematically balanced against the undeniable lives saved by early detection.
And cervical cancer screening is undergoing a massive, fascinating technological and epidemiological shift right now.
It truly is. For decades, the traditional pap smear, which involves looking at cells under a microscope for morphological changes, was the standard. Now, it is being rapidly replaced by primary HPV DNA testing, which is much more automated, highly sensitive, and efficient. But the real epidemiological game changer is the HPV vaccine.
Right. Because we are successfully vaccinating entire cohorts of young people against the virus that causes the cancer.
Yes. And as those highly vaccinated cohorts age into their 20s and 30s, the baseline prevalence of cervical cancer in the population is going to plummet. It is a massive public health victory. But remember Bayes' theorem and the iron law of screening.
Prevalence drives PPV. As the prevalence of cervical cancer drops toward zero, the positive predictive value of our screening tests will also plummet.
Exactly. The false positive ratio will soar. We will soon face the incredibly difficult, highly politicized task of scaling down, spacing out, or potentially starving cervical screening programs for vaccinated cohorts. And public health officials will have to battle that immense institutional inertia and the popularity paradox we discussed earlier, trying to convince the public that doing less screening is actually the safer, more scientifically sound path.
And finally, we have to mention prostate cancer and the infamous PSA test.
Prostate-specific antigen testing is perhaps the most universally controversial topic in all of screening. As epidemiological studies repeatedly note, men very frequently die with prostate cancer, not of it. It is frequently an incredibly slow-growing disease, the ultimate turtle.
So widespread screening would trigger massive overdiagnosis.
Immense overdiagnosis. Mass PSA screening inevitably leads to hundreds of thousands of unnecessary biopsies, surgeries, and radiation treatments that carry severe, life-altering side effects like impotence and incontinence. And all of that harm is inflicted to treat a slow-growing cancer that likely would never have naturally shortened the patient's life. Therefore, organized, systematic population screening for prostate cancer is generally not recommended by most major national guidelines, though individual opportunistic testing based on shared decision-making remains very common.
Wow. We have covered an absolute mountain of conceptual ground today. From the tightly controlled, randomized, heavily blinded, statistically rigorous world of intervention trials in the wind tunnel to the messy, economically fraught, and highly impactful world of population screening. You, the listener, have seen how changing an exposure changes an outcome, but only if that change is applied with absolute academic precision, intention to treat math to prevent bias, and unyielding ethical oversight.
We have journeyed from theory to practice. Observational studies suggest associations. Intervention trials rigorously test them. And population screening weaponizes those proven interventions, but it demands a profound, almost humble respect for the fundamental paradox of testing perfectly healthy people.
Which leaves you with a final, provocative thought to mull over. Think about the technological world we are entering right at this very moment. With the explosion of consumer genetics, ubiquitous 23andMe testing, and continuous biometric monitoring via smartwatches, rings, and wearables, the rigid line between an isolated controlled clinical trial and lifelong population screening is blurring entirely.
It is a profound, almost terrifying shift. We are moving away from episodic, systematic screening planned by governments and accelerating into an era of continuous, unregulated, opportunistic surveillance driven by consumer tech companies.
If your smartwatch is monitoring your precise heart rhythm, your blood oxygen saturation, your respiratory rate, and your temperature 24/7, are we slowly, inadvertently becoming a society of continuous patience before we ever feel a single physical symptom? What happens to the popularity paradox and the overwhelming burden on the healthcare system when an aggressive algorithm on your wrist is the one overdiagnosing you, sending you panicking to the emergency room for every minor, entirely benign physiological fluctuation?
That is a staggering public health challenge that the brilliant Wilson and Jungner criteria of 1968 could never possibly have anticipated. It is going to require a completely new, robust, ethical, and epidemiological framework for the 21st century.
Definitely something to explore on your own. Now, to lock in the massive amount of conceptual architecture we've unpacked today, our expert is going to take over for a high-yield recall session.
Let's test your pattern recognition and consolidate these frameworks. I will ask a question, pause briefly to let you think, and then provide the answer. Question 1. Which highly efficient trial design allows investigators to test two completely different interventions simultaneously on the same population, proving not only their individual efficacy but also whether their effects are additive? Answer: the factorial design. Revisit section 5.7, trial designs. Question 2. What is the specific mathematical term for the phenomenon where the required sample size of a trial balloons exponentially to maintain statistical power when participants drop out of the treatment arm or drop into the control arm? Answer: Latchin's correction factor. Revisit section 5.7, sample size and adherence. Question 3. In the context of trial analysis, what rigorous methodology requires that participants be analyzed exactly in the group they were originally assigned to, even if they completely failed to adhere to the protocol, in order to preserve the original randomization balance? Answer: intention to treat analysis, or ITT. Revisit section 5.7, analysis issues. Question 4. In population screening, which specific statistical metric answers the question, what is the probability that I actually have the disease given that my test result is positive, and is heavily dependent on the baseline prevalence of the disease? Answer: positive predictive value, or PPV. Revisit this section 11.4, properties of screening tests. Question 5. What specific epidemiological illusion occurs when a screening test appears to dramatically improve a patient's survival time, but in objective reality, it has only advanced the date of diagnosis without altering the ultimate clinical course or the final date of death? Answer: lead time bias. Revisit section 11.4, cancer screening. Question 6. According to public health experts Raffel and Gray, what dark paradox describes a situation where a highly inaccurate, harmful screening program that causes massive overdiagnosis of benign conditions actually gains intense, passionate public support? Answer: the popularity paradox. Revisit section 11.4, evaluating, restricting, and stopping existing programs.
Fantastic work. Thank you for joining us on this deep dive into the architecture of medical truth. Here are the details of this episode.
Methodology of intervention trials in individuals. Byline: from hypothesis to experiment testing causation under controlled conditions. Episode description: observational studies suggest associations. Intervention trials test them. This chapter examines the methodology of individual-level intervention trials, most notably the randomized controlled trial, RCT, often regarded as the gold standard for evaluating effectiveness. We explore the core components of trial design. Randomization to minimize confounding. We explore the core components of trial design. Allocation concealment. We explore the core components of trial design. Blinding of participants and investigators. We explore the core components of trial design. Standardized outcome measurement. We explore the core components of trial design. Intention to treat analysis. We explore the core components of trial design. Randomization is the central methodological innovation. By distributing known and unknown confounders evenly between groups, it strengthens causal inference. We explore the core components of trial design. The chapter also discusses ethical considerations, informed consent, equipoise, and risk-benefit assessment, as well as practical challenges such as recruitment, adherence, and attrition. We explore the core components of trial design. Trial phases, pragmatic versus explanatory designs, and issues of generalizability are examined. We explore the core components of trial design. While powerful, individual trials are not without limitations. They can be costly, may not reflect real-world conditions, and sometimes exclude vulnerable populations. We explore the core components of trial design. Nonetheless, when rigorously designed, intervention trials provide the strongest evidence that changing exposure changes outcome. We explore the core components of trial design. They transform epidemiological reasoning into experimental proof. We explore the core components of trial design. Key takeaways. We explore the core components of trial design. Randomization reduces confounding. We explore the core components of trial design. Allocation concealment and blinding minimize bias. We explore the core components of trial design. And intention to treat preserves comparability. We explore the core components of trial design. Ethical oversight is fundamental. We explore the core components on trial design. Trials can be explanatory or pragmatic. We explore the core components of trial design. Generalizability must be considered. We explore the core components of trial design. Recruitment and adherence affect validity. We explore the core components of trial design. RCTs provide strong causal evidence.